Okay, answers from our first quiz. So we have on problem number 1. Oh, remember the breakdown of this I've gone over in class. People that got more than a 95, there were 6. Between a 90 and a 95 were 5. 85 and 90 were 3. 80 and 85 were 2. 70 and 80 were 5. 65 to 70 were 2. And lower than 65 was 4 people. Okay, so let's go over this quiz. So for the first problem, we have to find the limit numerically. Now, if we did try to find this limit analytically, what we could do is rationalize out the numerator. And when we do that, we would multiply square root of x plus 5 minus 3 by the product that would make it a product of perfect squares. So, or use that. So we can do the first term. So we know that we would have this term squared minus the quantity of this term squared. So when we do that, what we get is x plus 5 minus 9. And that would give us plus 5, and minus 9 is minus 4. And so we would have an x minus 4 on the top and an x minus 4 on the bottom. Both of those would cancel, and we would get the limit of 1 over square root of x plus 5 plus 3. Now, if we were to do direct substitution into this, we wouldn't get any division by 0 or anything like that. So we could actually do that, and our direct substitution would yield 1 over the square root of 9 plus 3. Square root of 9 is 3, so it would be the same thing as 1 over 6. So analytically, this quantity should approach 1 over 6, which is 0.16666 repeating. And if you were to put it into your calculator, right, and you can see here I accidentally messed up on a decimal place there. I wrote it down wrong as I looked at it on the calculator. You should see that our number approaches closer and closer to 0.16 repeating. Okay, so in the next problem, we should have known, because we had done this from lecture, that sine of x over x is equal to 1. So as you get closer and closer to the value of 0, and closer would be values of 0.01, 0.001, 0.0001, and on the other side, negative 0.01, negative 0.0001, negative 0.0001, etc., until you come close to a value of 0. You should be coming closer and closer to a value of 1, which looks just like 0.9 repeating. Now, if some of you did not get this answer, there was a reason for that, and that reason was that the values that you were putting into sine of x may not have been radian quantities, but degree quantities. One thing that you can do to verify whether or not this was true or not is if you hit the mode button on your calculator, there'll be a screen, and then one of the selections on that will be radians and degrees. And if degrees is highlighted and radians is not under the mode menu, then you would get the wrong answer for this problem, because sine of x will not return the correct values unless you have it in radian mode. So if you had this happen to you, come up and talk to me, and we'll talk a little bit further. So on the next problem, let's see here. So okay. One moment. Okay, the next problem. Alright. So, in number 3, it says f of x is an arbitrary function shown below with a limit point of c comma l. So this point right here is the value when I say limit point. And I say if epsilon equals 1, then you are asked to draw what the maximum value of delta could be. Now, we keep in mind that epsilon can be any value which is L, or our y value of our limit point, plus epsilon, and then L minus epsilon, right? Those are the values that f of x has to stay between if you provide me with a value of delta. What I mean by that is if we were to zoom in on this picture, right? If I choose the width of my box, every single value of the function is guaranteed to be above or below that value, right? So if I give you a window which is wider graphically than the picture that I provide, maybe let's say outside of here or here, like I provide you with a delta on either side equal that is larger than the value that is shown here, then I can provide you with values of the function which go above or below this height that is provided. So for example, this value right here is a value for the function defined within the range of c minus delta and c plus delta, and it's outside of the allowed values of f of x. So we had talked about this in class a little bit more. Now if you had said anything like that, then you would also get full credit for number 4. So describe below how you would choose a value for delta. Draw a zoom-in sketch of the function on the x interval of the c minus delta to c plus delta and the y interval of L minus epsilon to L plus epsilon to reinforce your statement. So I said I choose this value of delta because the function is contained within the height of the box. Right? So that means when I say contained within the height of the box, that means that every value of the function is either greater than L minus epsilon or it's less than L plus epsilon. And that's part of the criterion for delta epsilon proofs. Okay, so number 5. The graph of the function f of x equal to x squared plus 1 is shown in the figure. Find an approximate numerical value of delta greater than 0 such that if the absolute value of x minus 1 is less than delta, or that you choose some interval that you stay between or a distance of no more than delta away from 1 on either side, then that guarantees that the value of f of x minus 2, which is what we say that this function approaches a value of 2 as x approaches 1, is going to be less than an epsilon value of 0.2. Show the work to the right of the graph. And this is exactly like the problem that was displayed on the homework. I think maybe the epsilon value might be different, or this value might be different, but it's exactly the same. So you can try to find what the function equals at the endpoints, or when epsilon is equal to either end of this, right? I didn't say that you had to find the maximum delta. I said that you could choose any delta that works. So one of the easier ways to do this is just choose a really, really small delta and see if the endpoints of that stay within the function, and then graphically determine whether or not it stays less than that the whole time. Or we can use the reasoning that we used in class. So I said let delta equal 1 over 1,000, and I chose this arbitrarily, and I just wanted to see whether or not it was true or not, right? So I said then if that's true, we get to assume this, right? We get to assume that the quantity, the absolute value of x minus 1 has to be less than 1 over 1,000. So if that is true, right, then this quantity, which is f of x minus 2 less than 0.2, is this right here. Okay, so we simplify it a little bit, right, and we get x squared minus 1. The absolute value of x squared minus 1 is the same thing as the absolute value of x plus 1 times the absolute value of x minus 1. So this quantity right here has to be less than 1 over 1,000, right? So that's true, and we throw that in. Now, that means that x as a value, right, can be no greater than 1 over 1,000, or excuse me, x can be no value which is greater than 1 plus 1 over 1,000, right? So that's the largest that we can go to the right, right? And even this is too big on this scale, right? But I just choose this arbitrarily. And so that means that x plus 1 can be no greater than 1001 over 1000, right? So this quantity, because we chose a certain delta, 1 over 1000, this quantity of the absolute value of x plus 1 could be no greater than 1.001. So therefore, this whole thing, right, can be no greater than those two things multiplied together, and then therefore, when we multiply these two things together, we get this, which is equal to this, and clearly that is less than 0.2. So we know that anywhere in our little range of 1 plus 1 over 1000 and 1 minus 1 over 1000 will guarantee that our function will remain less than 0.2, and even much less than 0.2. And that's a harder one, and one person got this question out of the entire class. So if you didn't get it, don't feel too bad, but if you are going to continue on with math, you will see these kind of things a little bit later, and so look it up. There are a couple different places that you can go a little bit further than this. One is if you, and I'm going to talk about it in class, there's a nice series of examples on this from the Khan Academy, which is spelled Khan Academy, and I'm going to provide a link for that too. Okay, so I won't devote any more time to epsilon delta after this point, but I do want you to get the gist and the idea. Okay, let's continue on to the next problem. You know what? Why don't we put it in a separate video? Okay, so that's the first two pages, and I'll go over the rest in a little bit.